Hello and welcome again to another video, and today we're finally doing it. We're going to be doing a memory allocator in 8080 assembly. And now the thing is, a simple memory allocator isn't really that difficult. Truly, if you want to have everything stripped down to the very bare essentials, it's literally like 6 lines of code. Like 6 instructions. That's all it is. The memory allocator, the difficulty of it, is all in how you implement it. How many checks do you do for it? How safe is it? Is there a garbage collection? Do you have part of a linked list? All that sort of thing. Today we're doing a very simple memory allocator. I'm just going to call alloc instead of malloc, but whatever. Normally you would do a linked list or a doubly linked list for this sort of thing. This is neither. This is more of a map. In fact, you don't even need to have a map, although a map is very good. What's going to happen is we're going to have a portion at the end of the program dedicated for a map of pointers to the rest of the memory that's free in CPM, and you can go up and down that pointer list, and that's going to be your pointers to the blocks of memory that you've allocated. And truly, it's really up to you on how to implement this. But I'm going to show you the very bare essentials on how a memory allocator works in 8080 assembly. I pulled this from the original C book from Kerrigan and Ritchie, I think. And Kerrigan and Ritchie, yes. The very first C book, they have a nice alloc and a free function. I don't agree with the free functionality. I mean, it works, but it's, you'll see. Okay, let's start the boilerplate. 5 put string equals 9, all the good stuff. And then line, or end of line, let's do $sign. I still have no idea why CPM chose the $sign. Then what we're going to be doing is we're going to make your heap storage defined. So heap pointer size, so 32. So I'm going to have 16 entries available for pointers, for your heap pointers. And then alloc buff, this is going to be the your alloc buffer. And we're going to use the sets because this is a forward reference. Prog end plus heap pointer size. So at the very end, so we're going to have org 100h start. Wow. I need to change that syntax. The very end, we're going to have prog end. Okay, so this is where the program is going to end, and between prog end and heap pointer size, we're going to have the table of pointers, and then after that, it's free game. It is free memory for you to use. Okay. Now, let's get coding. So start. We're going to first alloc h alloc buff. We're going to load alloc buff into h, and we're going to shld alloc p. And what is alloc p? Alloc p is 2 bytes. It is a pointer. Memory allocator pointer. This is going to be a pointer that points to where the current free chunk is. And free is going to be in massive quotes because it's going to be up to you to determine whether it's free or not. And we're going to store it to alloc p. Okay. And then I want to just allocate 16 bytes of memory. So let's do that. Let's do alloc b. We're going to do 16. And then call alloc. And alloc is going to be the malloc, right? Cool. And then, so allocate 16 bytes of memory. But then I kind of want to allocate 16 more bytes of memory just so I can show you that this pointer tomfoolery actually works. So we're going to allocate a 16-byte chunk and then another 16-byte chunk. Now, why will just allocating a 16-byte chunk not prove anything? Let me show you. If we go down to alloc, we're going to load HLD, alloc-p. Now, LHLD and SHLD takes 16 clock cycles. So we're going to load alloc-p. We're going to load the alloc pointer. Okay. We're going to do move H to D, and we're going to move L to E. Okay. Copy to DE. I could use an exchange and a load, but that is slower. I'm trying to keep that in mind, especially when I'm like making up my 8080 roguelike. I'm just trying to keep in mind exactly the speed of what I'm doing. Anyway, so I've copied to DE, and we're going to add B. Add memory offset. And then we're going to store it back to alloc-p. And then we're going to do an exchange. So HL is now old alloc-p. And return. Now, what did I just do, and why does this work? Let me scroll down here and let me show you. One moment. So first of all, when the program starts, alloc-p points to the very beginning of your free memory. The free memory is all the way from the end of your program, right here, all the way up to the command control processor at the end. And after that is the BDOS and the BIOS and all that. What ends up happening is when you allocate something, I will allocate X amount of bytes, but the pointer that I want to return starts where alloc-p was, not where it's now. Then, after an alloc-p call, alloc-p will now start here, and then I'll allocate a set amount of bytes, and that pointer will return to at the end of it. So this first 16-byte allocation, while it technically does something, it doesn't do anything to the alloc-p pointer. I need to do another allocation to get the updated pointer, just to prove that this actually works. That is how this memory allocator works. And then for free, it's a really dirty free. There's no checking for anything. All free will do is just, you will pass in a pointer into free, and it will set and say like, oh, the free allocation is right here. And it could be right in the middle of, data that you need or something, and it's absolutely garbage. Now, the Kerrigan and Ritchie book has a check to see whether or not it's within the bounds, whether or not your pointers are within the bounds of the acceptable range. They have a local heap to the program. It's really not a local heap, but whatever. I'm using just open heap. It's the garbage memory in the computer anyway. Ideally, you would be using the entire, you would know the end of your transient program memory, and you would have to check, okay, is the pointer in between the end of my program and the TPA limit? If it's within that, then it'll be good. Is the memory I've already allocated? Are there pointers there? Are there pointers with an amount of size there? That's for much later, and that's beyond the scope of this video. And honestly, I haven't figured out how to do it in 8080 assembly. I haven't needed to in 8080 assembly. Not yet, but anyway. That right there is the overview of how this memory allocator works. So anyway, I have now allocated the 16-byte chunk, and now what happens? I want to copy a string to it. So let's do lxid message, and the message, of course, is just going to be down here. It's going to be msg db. We're just going to do hello world. Okay. And I want to copy de, right, message to hl, which is going to be what the alloc returns. Then call, oh my god, call string copy. Okay. Okay, call string copy. And then string copy will return the destination of what I copied to. So I want to store end dirty store of pointer to end plus 0. Because there's only one pointer, the offset 0 is going to be nothing. If I had another pointer, I would be doing prog_end plus 2 plus 4. That's what the heap pointer would be for. Anyway, let's carry on. So now I have a pointer located at the end of my program, okay, pointing to somewhere else in memory to a string that I have just copied. So let's print it out. Okay, let's do it. So we're going to load HLD prog_end. Okay, we're going to exchange it because de call put s and return. That's it. So we should see hello world printed out. And let us continue on our way. So just to show you exactly how disgusting free is, we're gonna show you free. Move so basically you would do an LXI pointer or like an SHLD to, you would load your pointer into BC, you move it to HL, SHLD, alloc_p, and return. That's exactly how disgusting free would be in this case. But of course, that's not what you want to do. You want to do things much better, much more in the right way. So string copy. So we're going to push H. We're going to pop H to preserve it. We're going to first exchange. We're going to move M to A. Going to see if it's the end of line. If it is, then string copy end. If not, we're going to exchange back and move the accumulator to memory location. We're going to increment D, we're going to increment H, and jump string copy +1 to skip that push H. And of course, we're going to string copy end. Can exchange back, move the end of line to the end there, pop H, and return. And of course, we need our put S. Okay. Let's try this out. It worked. As you can see, I have hello world being printed, and I think if I call this again, it works again. So I've allocated 3 blocks of memory, and only in the last memory have I copied hello world to it, and I then print hello world from that last block that I've copied. If I really wanted to, I could do something like this. I could do SHLD. Basically, what you would do is you would do SHLD prog end plus offset, and then offset would be offset. So at the very beginning, you would say offset equals 0, okay? And then after allocating something, you would do offset plus plus. And then you would just copy this after every single alloc. Or you could put it inside the alloc just so that you could have, you know, this is going to be the next bit in the table. It's going to be the next bit in the table that points to memory. And then free, you would decrement the offset to say, okay, now I'm going to go back one. But again, that's if your free is any good. So anyway, that there is a memory allocator in 8080 assembly. As you can see, it's very easy to implement, or it's very easy to get quick down and dirty and do, but it's a whole other beast on how to implement it correctly. How do you do garbage collection? How do you do the linked list, double linked list, all that sort of thing. And yeah, in the future I may revisit this in a linked list format. I would love to. I think that'd be really cool. But just for now, this works just fine. And I will see you in the next one.